before galaxies formed, stars ignited, something left a mark on the universe. Not with fire, not with matter, but in light. There is something in the oldest light of cosmos that should not be there. Not a galaxy, not a black hole, not an explosion. A region slightly colder than it should be, not by much, but enough to matter. To understand why that faint mark exists, we have to return to the moment the universe first became transparent, the moment light was finally allowed to travel freely. For nearly 380,000 years after the Big Bang, the universe was not empty space. It was a glowing fog, a dense, hot plasma where particles and light were entangled together. Electrons and protons moved freely. Photons tried to travel, but they kept colliding. Every step forward ended in another collision. Light could not move far. The universe was bright, but shielded. Then something changed. As the cosmos expanded, it cooled. When the temperature dropped below about 3000 Kelvin, electrons slowed enough to protons to capture them. Neutral hydrogen formed, and in that quiet transition, the universe changed state. Light was not created in that moment. It was released, freed from the constant collision. Photons began to travel across space without interruption. For 13.8 billion years, they have continued that journey. But space itself was stretching. As the universe expanded, their wavelength stretched with it. What began as a visual light lengthened into microwaves. The temperature cooled just to 2.725 degrees above absolute zero. Today, that ancient radiation surrounds us in every direction. We call it the cosmic microwave background. It is the first light, the earliest surface we will ever observe. And when we map that surface with precision, something extraordinary appears. The universe is almost perfectly uniform. Across the entire sky, the temperature varies by only 1 part in 100,000. Almost, because in one region, towards the constellation Uranus, the temperature dips slightly lower than expected. Not dramatically, not violently, but measurably. A subtle deviation, a faint irregularity, a quiet scar in the first light, the cold spot. The earlier universe was extraordinarily smooth. Not perfectly smooth, but almost. If you could see the microwave background as a temperature map, the difference would be tiny. About 100 microkelvin, less than 1,000 of a degree. So small, they seem meaningless. And yet, from those tiny differences, everything formed. When the temperature was slightly higher, matter was slightly denser. When the matter was slightly denser, gravity pulled them a little harder. Over billions of years, those small advantages grew. Clouds collapsed, stars ignited, galaxies assembled, and the cosmic web emerged. Everything began as a fluctuation almost too small to notice, but those fluctuations follows rules. They are random, but random in a precise way. Statistically, they form what physicists call a Gaussian distribution. Most variations are small, extremes one are rare, no direction is preferred. No side of the universe is heavier, no hemisphere dominates, no X tilts the cosmos. On the largest scales, the universe does not lean. These expectations come from the inflation, a phase of exponential expansion less than a second after the Big Bang. Space did not simply expand, it expanded exponentially. In a fraction of a second, space stretched faster than light, stretching microscopic quantum fluctuations to astronomical scales. Inflation smoothed curvature, erased large asymmetries, left behind a universe that should be balanced. No cosmic center, no preferred direction, which is why even a small imbalance matters. In 2004, the Olson microentropy probe mapped the microwave background with unexpected precision. It measured temperature difference measured in millionths of a degree. The data confirmed inflation with remarkable accuracy, except in one place. In the direction of Uranus, a patch of sky 5 to 10 degrees wide, about 20 times the apparent width of the full moon, appeared colder than average by about 150 to 200 microkelvin. That may sound small, but the entire background fluctuations only about 100 microkelvin. This dip was deeper than the typical variation. Statistically rare, roughly 1% probability under standard cosmology. Unlikely but possible. An anomaly can be tolerated once. Then came the Planck satellite, higher sensitivity, better resolution, independent measurement. If the cold spot were a mistake, Planck should have erased it. But it did not. The same reason remained. Same location, same scale, same depth. When independent measurement reproduced the same irregularity in the radiation emitted 13.8 billion years ago, coincidence become harder to defend. The anomaly stops being feeling accidental. It begins to feel real. To understand what could create such a reason, imagine a photon released at recombination, leaving the surface of the last scattering and beginning its journey, not through emptiness, but through evolving space-time. Galaxies ignited, clusters collided, vast underdense region, cosmic void, open across hundreds of millions, even billions of light years. Gravity shapes this terrain, where matter gathers, space-time carved inward. Where matter scatters, the carve is shallow. A photon falling into a gravitational well gains energy. Climbing out, it loses that energy. If universe was static, the exchange would be perfectly balanced, down, up, equal. But the universe is not static. Expansion is accelerating. Dark energy causes gravitational potential to weaken over time. When a photon enters a massive void, it falls into a shallow gravitational depression and gains energy. But as it exits, the void has expanded. Its gravitational pull has weakened. The climb out is no longer equal to the fall in. A small imbalance remains, accumulated across billions of years. This effect, the integrated Sachs-Wolfe effect, leaves measurable imprint in the microwave background. In the direction of the cold spot lies the irredenous supervoid, spanning nearly 2 billion light years across. A structure of that scale should cool passing photons, and it does, but not by full absorbed amount. Structure explains part of the anomaly, not all of it. If late-time cosmic structure cannot fully account for the cold spot, the explanation must reach further back. Before galaxies, before atoms, before transparency, into the inflation itself. Inflation was exponential expansion, space doubling again and again in intervals almost unimaginably small. In less than a second, the universe expanded from microscopic scale to astronomical size. Tiny quantum fluctuation was stretched outward. Microscopic irregularities become cosmic seeds. Standard inflation predicts those fluctuations should be nearly Gaussian, nearly uniform, no predicted direction, balanced. But some extended models allow a more complex picture. Inflation may not have ended everywhere at the same time. Separate regions of spacetime could have expanded independently. If two such regions interacted, if inflating domains collided, the boundary between them could have left a circular imprint in the microwave background. No debris, no flame, but a localized deviation, a gentle break in statistical symmetry, written into the first light. This hypothesis is speculative. The cold spot does not require it. A rare fluctuation remains mathematically possible, yet the scale and the presence of the anomaly keeps the question open, because asymmetry at the cosmic scales is fragile. Even smallest deviation carries weight. We are talking about a temperature difference smaller than 1,000th of a degree, spreading across a region billions of light years wide, encoded in photons older than every star in the sky, measured by instrument orbiting a planet that did not exist when the signal began. Pause for a moment. Really think about that scale. You are looking at a map of the universe when it was 380,000 years old. And on that map, there is a cold depression. Long before galaxies formed, something disturbed the symmetry of the universe, and the mark never fully faded. Not violent, not dramatic, just persistent. A quiet irregularity in the first light. And when the scene fades, what remains is not fear, it is awe. The universe is nearly perfect. Nearly. And somewhere in the tension glow, a scar remains.